We will be discussing today the behavior of electromagnetic waves in a conducting media. We have already discussed the behavior of electromagnetic waves in a general matter and in the non-conducting media before. So today we will be limiting ourselves to the conductors with obey Ohm's law, that is ohmic conductors. And in such conductors, the current density is given by the product of the conductivity and the electric vector E. Under these circumstances, the four Maxwell's equations takes this form, like represented in equations 5 to 8. And we again take the curl of the equation 7 and substitute the value of curl B from equation 8. We arrive at a second order equation having both the space and the time of varying operators. That equation can be rewritten as, and to solve this equation, we consider and assume the solution of the form given by equation 13. And when you substitute this value of the electric vector into the differential equation given by equation 12 and perform the operation, differential operations, we arrive at the equation 14, which is a second order equation, relation between omega and k, and is called the dispersion relation. To find the value of the k from the dispersion relation, we know that the k is a complex quantity, the wave vector is a complex quantity, and we take it to be of the form of alpha minus j beta as represented by equation 15, where alpha is the real part and beta is the imaginary part. And we substitute this value of wave vector from equation 15 to the dispersion relation and equate the real and imaginary parts on both the sides. We get the value of the real and imaginary parts of alpha and beta as given by equation 16 and 17. This is simple mathematics. The electric field, like I said, that the K is a complex quantity. And if we substitute this value of K given by equation 15 into the electric field as represented by equation 13, we can say that the electric vector now takes the form represented by this equation 18, where we have two terms, oscillatory terms. One is oscillating, when you can see that J here, and here this term is independent of J. So this term, which is dependent on J, results in the propagation or the behavior of the wave like in other matter, but the second term is responsible for the decay of the wave. And since this is an exponential term, so the wave will decay exponentially. You can see this is the origin or the interface at which the wave enters in the medium, and its intensity decreases exponentially and becomes zero at a certain distance. We will discuss about this decay while discussing skin depth in the next lecture. And in a simple non-conducting medium, like we discussed in a previous class, there was no decay as such. But in the conducting medium, the wave will decay, and the length with which it can penetrate without decaying or decaying up to certain ratio of the incident wave, that we will discuss in the next lecture. Like we just saw the behavior of the electric vector here, we can say that the magnetic vector will also behave in a similar fashion. So we can have the value of the magnetic vector represented by equation 19. And the electric and magnetic vectors are related by the Maxwell's equation. So we get the relation between the two vectors as in equation 22. So we can see that in a non-conducting medium, both the electric and magnetic vectors are perpendicular to each other, but there is a phase difference between the two. In a non-conducting medium, there was no phase difference. So, and here the phase difference is the ratio of the imaginary to the real part of the propagation vector. So this is the electric vector that we saw earlier. And if we consider the direction of propagation to be the plus z direction, then the electric field can be represented as in equation 33. And for a fixed phase, this term omega t minus alpha z should be a constant quantity, which on differentiation gives the phase velocity. And we can also say that the electric vector is a electric field rather is a superposition of two waves having equal amplitudes. So we have the two waves. One wave is with omega plus and the other oscillates with the frequency omega minus, and they will superimpose to give a wave with a frequency omega. X being the direction of the electric vector and Z being the direction of the propagation. We use the trigonometric identity cos A plus cos B, and this equation 40 now reduces to 42, where omega 0 and delta omega are these two quantities. So this equation 42 can be rewritten as this. This is the same equation, we haven't done anything. And the phase velocity, as we saw earlier, and the group velocity can be written as delta omega upon delta k, or d omega by dk, as we have studied earlier while discussing the waves and oscillations. So here you can see that the red waves moves with the phase velocity Vp, and blue is the modulation wave that travels with the group velocity Vg. Now today we discussed the behavior of the electric and magnetic fields in a conducting medium, with a propagation vector being a complex quantity, and we noticed that the waves travels like in a non-conducting medium, but there is a decay term which results in an exponential decay of the wave, and this decay is exponential, but we define a term skin depth to study the nature of the decay, and that will be our next lecture. So today I end here. Thank you.